Hello everyone, I am Aisha Banu and today I am going to talk about the particle in one-dimensional potential well. It is a fundamental concept in quantum mechanics, and in this video we will explore how energy becomes quantized due to the boundary conditions. So let us start. First of all, let us know what is a potential well. It is a region in which a particle is confined. When a particle is confined in a very small region like inside a box with infinite potential walls, it cannot have energy. This leads to discrete or quantized energy levels. This model helps us to understand the behavior of electrons and other particles in small spaces. Let us assume a particle of mass m, which is trapped in a one-dimensional box of length a. Inside the box, the potential energy is zero, so the particle is free to move. But at the edges, the potential becomes infinite, so the particle is strictly confined between 0 and a. You can observe this clearly in this picture. These conditions force its wave function to be 0 at the boundaries. From Schrodinger's time-independent equation, which is shown here. In one-dimensional box, the potential energy is 0, and when we substitute V has a 0 in Schrodinger equation, we get this equation 1. And let us assume that k square is equals to 2me by h cut square. Then the Schrodinger's equation will become like this. And there are some boundary conditions to solve this Schrodinger's time equation. They are x is equals to 0, chi of x is equals to 0. And x is equals to a, chi of x is equals to 0. These conditions helps us to solve this Schrodinger time equation, and when we solve this Schrodinger time equation, we understand that particles' energy levels are not continuous, they are quantized. The energy of the particle is measured by following these steps. As we know that k square is equals to 2me by h cut square. From this, E is equals to k square h cut square by 2m. We have k is equals to n pi by a. By substituting it in this equation, we get the overall energy as n square h square by 8ma square, where n is a positive integer such as 1, 2, 3 and so on. Each value of n corresponds to a different energy level. Let us take a specific example. For n is equals to 1, the lowest energy, we get E1 is equals to h square by 8ma square. Similarly, for n is equals to 0, we get 4h square by 8ma square, which is equals to 4E1. And for n is equals to 3, E3 is 9h square by 8ma square, that is similar to 9E1. And similarly, for n is equals to 4, E4 is equals to 16h square by 8ma square, and that is equals to 16E1. So the spacing between nth energy level and the next higher level increases as n plus 1 whole square E1 minus n square E1 is equals to 2n plus 1 E1. This means the higher the level, the greater the spacing between it and the next one. This is very different from classical systems where spacing could be uniform and continuous. Here is a visual of those energy levels. As we can see, the first level is E1. It is at the lowest. Then comes E2. That is equals to 4E1. Then E3 is equals to 9E1. The lines get farther apart as we go up, showing the increasing energy spacing. These energy levels are called eigenvalues, and each corresponds to a standing wave solution of the particle's wave function inside the box. Some key points to summarize the topic are: particle can't have any kind of energy, it can have only quantized values, and these values are known as eigenvalues. Energy levels get farther apart at higher n, the spacing between the levels increases with n. This concept is essential in understanding the quantum systems and devices. Thank you so much for your patient listening.